Hi, welcome back to AP Physics C, Electricity and Magnetism. In this particular video, we're going to look at what happens when we need to induce an electromotive force on a wire. So the first thing, in the last video, we talked about magnetic flux. So just a reminder that magnetic flux will be defined as the amount of magnetic field that flows right through an area. So like right now in that statement, the magnetic field is stationary, right? So it's not moving. So what happens is any change in the magnetic environment will cause the voltage or the EMF to be induced in the coil. This is where Michael Faraday comes into play, because he has a law that establishes the mathematical relationship between the EMF and the change in the magnetic flux. And that law is EMF equals negative N, right? So N being the number of turns, d phi dt. So remember, phi, sometimes we write a subscript b. This is our magnetic flux. And when you see that d, the derivative notation, that means something's changing. And so that's telling us that the magnetic flux is changing with respect to time. N is the number of turns, right? Especially if this was a solenoid. You would need to know how many turns are there that are hitting it, or that are there in the solenoid. So then you have to just kind of address that negative sign, right? So that negative sign is addressed with Lenz's law. Okay, it says that the change in magnetic flux induces currents in a direction that opposes the change that caused it. So Lenz's law is the reason why there is a negative sign in Faraday's law. Okay, and then so that kind of brings us over to these diagrams of these magnets and velocities happening. Okay, so if we look at the first one, ultimately the goal is going to be like, which direction is the magnetic field induced, or which way is the current going to go? So when you have, and what happens is the current carrying wire is going to produce a magnetic field to essentially like help it, or to stop it from, to stop those fields, right? And so from the magnet, in our first top left, right, we're going to have a downward magnetic field from the magnet itself. And so what we need to do is try to determine which way is that field going to induce. Okay, so what happens is the field, or the wire, it's like it's going to stick a magnet itself, right, to stop that magnetic field. So it's going to produce an upward magnetic field. Okay, so this is B, right, from the magnet itself, and it is increasing because as you get closer, you get more field lines. So that means the magnetic field caused by the magnet is increasing. Okay, and then we have an induced field, right? Essentially, the wire wants to create something to cancel it out, right? And so we follow our rules, right? And we grab the wire, and that tells us that the induced current, right, will be traveling in a counterclockwise direction. Okay, so that it creates that upward, right, that upward induced magnetic field. Okay, so if you come into the next one, the one right below it, what happens is, again, we identify our field. So our field is going to be coming through, right, from the magnet, because it goes north to south. But in this case, B is going to be decreasing because my velocity tells me I'm pulling the magnet away, which then what happens is the wire creates a north, right, because now it wants it to come back, right, because it wants to maintain like a balance. So how does it balance it? Well, if I have a decreasing B, and then what I want to do is I want to create a magnetic field that matches that, right? So, stick with blue. right? And so the induced magnetic field from the wire will be down, okay? Because again, it's creating essentially a north pole in the face of the wire, right? And so if I grab my wire again, okay, this now will flow in a clockwise motion, all right? Now you go over to the one to the right, top right, so our velocity is down, our B field is coming through because we're going north to south, but because we're pushing the magnet through, right, B is increasing, okay, which again, what is the wire going to do? It's going to put up a north pole here because like it wants to, excuse me, it'll pull up a south pole, okay, because it wants to stop that increase, and I apologize. So that means we're going to have a downward induced current or downward induced B field, okay, which then again, follow my rules. I grab the wire, and what happens? We will have an induced current flowing in a clockwise manner, all right? And then we go to the last one. So now we're pushing that south up through the other end, right? So we're coming in this way. B will be increasing. Remember, we're increasing when the velocity, when the magnet is being pushed through the wire. So again, it's going to put up, the wire is going to put up a block essentially, right? So a south coming in. And so we'll have a B field induced downward. Okay. And then what happens? My current will flow in a counterclockwise manner. All right. And then the last thing in this slide, you'll get something called motional EMF. And so what happens is an EMF induced by motion relative to the magnetic field. It's called motional, and it's calculated by a simple formula. The EMF is BLV. Okay, and it's kind of this picture that you barely see down on the right. Okay, so it'll be a magnetic field, right? You're going to pull this rod through it, and then you're going to have, it's going to be separated, right, across the distance, and you just multiply all those numbers, and you'll get a motional EMF. Okay, so let's look at an example problem, right, pertaining to the induced EMF. And so here we got a magnetic field at a strength of that's given by B of t is 2t squared minus 2t plus 2, acts out of the plane of the page. A circular loop of radius r, which is of 2 meters within the page, has a field pass through it. So we're going to find the induced EMF in the wire as a function of time, and then we're going to find the direction of the current in the wire at 2 seconds. So we're going to find the induced EMF. So I know the equation, negative n d phi, right, dt. And remember, phi is BA, right? And so what we're going to essentially do is we know that there's going to be one wire or one turn, and I'm going to do dBA, right, dt. So my A is constant, so I can bring that out. So it's going to be A dB dt. Okay. And then now I'm just going to take the derivative, multiplied by A. Sorry, I forgot the negative signs. So of our function, 2t squared minus 2t plus 2. And so we're going to get negative A times, take the derivative of that. It's going to be 4t minus 2. And A is, they tell us A, well, they tell us the radius, so we know it's going to be pi r squared. All right, and so that's going to be pi times 2 squared times 4t minus 2. And so it ends up being negative, so this is 4 pi. So we get negative 16 pi t minus 8 pi. So that is the EMF, right, that's induced. And now we want to find the direction of the current at 2. And so what we do is we need to figure out, is the B field at that time increasing or decreasing? And so what we're going to do is we're going to take the derivative, which we already kind of did, right? We know that phi is dB dt. And so we're going to do, we know the answer is 4t minus 2, but what I'm going to do is at t, we're going to plug in 2. And if this number is positive, it's increasing at that time. If it's negative, then it's decreasing at that time. So this is positive 8. And so what that means is B is increasing at 2 seconds, right? And it's out of the page, right? That's what these circles mean, right? Out of the page. Therefore, is my symbol for therefore, the current is going to oppose this, therefore traveling clockwise, right? Because I've got increasing coming at me. That means it wants to create an inward, right, magnetic field. So I want it to go in. So then I wrap my fingers around. So in magnetic field, wrap them around, and that's the direction of the current. Okay. So I know, so Faraday's law, Lenz's law can lead to a lot of confusing scenarios, especially here with the wires. In the next video, we're going to look at inductance. So the inductance is going to lead to another type of circuit, which then is going to lead into finally Maxwell's equations, which are the last section here in AP Physics C.